Welcome to Hot Chips 25. Session 6, Networking.
Okay, folks, welcome to the networking session here at Hot Chips. We will have 2 talks in this session, followed directly by a keynote. The first presentation is by Michael Miller from Mosys. Michael is the Vice President of Technology, Innovation, and Systems Application for Mosys. Mike brings more than 30 years of experience in technology innovation, systems architecture, software, and complex logic. Prior to Mosys, he held positions as Chief Technology Officer for IDT. Welcome, Mike.
So good morning. I'm pleased to be here. I'm going to change, I think, sort of where we're at in the discussion. I think a lot of the previous discussions have been at a much higher sort of level, about algorithms, how you process packets, how you can accelerate those using FPGAs. And instead, talk about another particular aspect. And it seems that no matter how sophisticated and complex we get in the compute sort of area, we'll always run up against the bottleneck of getting to the memory. So how do we get things back and forth between the memory and the processor, which is executing particular algorithms? So today I'm going to talk about our second generation part. I think 2 years ago we talked about our first generation, but now we're on our second generation part, which now takes us to 4.5 billion accesses per second when you add together both the reads and the writes. So the vision that we have at Mosys is that if you look at the packet processor, it's going to multiple cores. And we do that to get the performance up and try to manage the power and get a lot more bandwidth internally. But then you have to be able to get to the memory. And the memory is going to be following the same sort of paradigm, I believe, which is more blocks of memory running in parallel. Now you got to get things back and forth. And so you could use parallel I/O, but if you look at the trend chart, you'll see that parallel I/O, while it's been increasing over time for memory, still goes at a fairly flat slope compared to what you see in terms of demand for packet processing and networking. So for Mosys, we decided then to go to a serial interface to be the way to then move the data back and forth at a very high rate and make use of electrical standards that are being developed for moving packets. So reprovision it for that particular area. So once you do that, however, you still notice that you have a lot of performance internally. I mean, I can add more blocks, get more accesses going, but those scarce I/O pins, even though we might be running them at 10 gigabits or 15 gigabits per second, still are the bottleneck. So one of the things that we've been working on, you'll see that in the presentation, is starting to add some more primitives internally to help make more of the given bandwidth that's transitioning between the 2 different devices. So the second generation part, I'll let you read this offline in a bit more detail, but this is a synopsis of our various devices. You'll notice our first generation there is the 576. The 3 devices that we call Bandwidth Engine Generation 2 then is what we're bringing out. And that breaks down into a part called the 820, which is kind of our flagship, and I'll talk at the end, where it's got a lot more functionality, and the 620, which is just a subset of that. So that's one sort of functional group of parts. The other one is the 720 that I'll talk about first, which is really aimed at performance when you're doing lots of reading and writing. So let's look at the functional design. And what you'll see here, starting at the top, is the SerDes coming into the device. going through what we call our GCI layer. It's a protocol layer that just ensures that you get packets reliably back and forth across the serial interface intact. And if you discover that there's an error, because we put a CRC in there, it can do a replay mechanism and do a precise healing of the packet flow. So you don't have to worry about packets, and packets, by that what I mean is memory references coming through reliably. Once you do that, then you get into the memory controller, which is then accessing 4 partitions. Each of those partitions are broken up into 64 individual banks. And we can then do 8 bank accesses spread across those 4 partitions. So 2 reads per partition and 2 writes per partition. And so internally we have 6 giga access of performance internally for doing reads and writes. And eventually those get collected back down and then go through the SerDes out back to the host device. So one of the interesting things, though, is when you start having lots of banks, you're running things in parallel, you have lots of threads that are going on in the processor, you could end up, for instance, in the scenario, if you're just doing lots of reads and writes, let's say 50% reads and writes, that unfortunately, maybe you start accessing the same bank at the same time. And so you could then drop to 50% of your performance if you're so unlucky. And that might be where you have a small FIFO, for instance, is just banging against empty all the time or banging against full. And so we wanted to address that particular case in this device that we call the 720. So we have something that we call the bank conflict resolution logic, which adds then a block of memory in the controller, a block for each of the partitions to resolve that particular case. And what it does is it creates this part we call the 720, and if you look at the memory partitions represented at the bottom of the device there, we talk about 4 very large banks. Well, what that is it's composed of those 64 banks, but we've hidden away the bankness, let's call it, by using this bank conflict resolution logic. So what we're doing here is that you can look at the memory partition here, and you can do this write with a flat partition, comes in here and then looks to see what's going on with the read flat partition, and then resolves any transitions that are going on in here. And I'll show you a little bit later the block diagram of what that is doing. But in effect, it allows for continuous, simultaneous read-write accesses of the memory. So at that point, with this, you can get up to then 3 billion operations composed of balanced reads and writes. The other block you see over here is really showing cycles of commands coming in here versus 8 lanes of command being received, 8 lanes of command being received, and showing how we can have a read command packed in here, a write command, all in the 72-bit word, followed by the data. And you can do this continuously, and then you can get on the output continuous data coming back out. So in essence, what that's doing is giving you then the functionality of a dual port memory. A QDR SRAM is a memory which you can read simultaneously, write simultaneously, and can even read and write the very same locations. And so it's a very nice property to have. With single-ported bank memory, you don't get that. So this is a block diagram that shows, in essence, the logic that we added then to achieve that particular functionality. So we call it a delayed write cache memory. And so whenever you're doing a write operation, you're always comparing it against the read. And you look at the bank addresses. If you happen to be wanting to write to a bank that's being read, then you write that particular word up into the delayed write cache. Now that means in whatever you read, you have to compare what you're reading against a traditional address tag with the bank address and see, is it in the cache or can I go get it from the memory? You know, where is the most recent copy? And so it'll do the right thing to pull the data out. And then if a write happens to, as we talked about, wants to write to the same bank that we're reading from, it will just write that into the delayed write cache. Now, you can then later figure out through logic here that if I'm writing into the cache and I'm doing a read from another bank, I can always retire each of the writes later on. So you can push things through this cache. And we call it a delayed write cache because it's kind of a little bit turning a paradigm on its head. Most people think of a cache as speeding up accesses, and they always think about it from the read sort of aspect. in this particular case, we're doing this direct map cache to just delay writes. Using the cache is kind of like a write buffer, but actually a very large one that happens to match the size of each of the banks. So a different twist on a old concept. But what it does then for us is it allows us, in the worst case, no matter what, to continuously be able to read and write without paying attention to what the banks are. Now, one of the things you might have noticed when you looked at the block diagram I showed you before, we had in each of the partitions, we could access 4 banks at a time, 2 reads and 2 writes. And the mechanism that I just showed you resolved a read port and a write port. And I said that we had 4 of those caches. So when you do the math, you say, well, but gee whiz, I can only now access or utilize half the ports that are going on in the memory. What happened? You talked about having lots of internal bandwidth. So one of the things that we allow for in this architecture is we allow the bank conflict resolution logic to be managing 2 of the ports, 1 read and 1 write, but we still allow access then on the other port, the other read and write port. Now, obviously, they can't participate in the coherency of the cache. But that's okay, because when you start thinking about applications, and from a packet processing, which is where we're really targeting this, you may have things like linked lists that you want to be able to do lots of reads and writes, but you may have some tables in the memory which are also just mainly read-only type tables where you're doing some sort of table locking, or maybe you're just indexing or just hashing. So by allowing these other ports, then you can partition the memory however you want for your linked list area, and then you can put your table lookup. And then doing that, then you can get the maximum benefit of all the different read-write ports internally to the memory. And we'll get back to the case then where it's just the SERDES and the command rates that then become the bottleneck again. So this diagram here is showing you then that application from the standpoint of sort of in a cartoon form, showing maybe you have 4 100 gig packet flows coming in, maybe over 4 100 gig links. And then you could have your processing engines that are processing those 100 gig. You then have enough bandwidth then to go down into each of the partitions, and maybe you map the partitions each to one of the ports. So you have, since we're cycling this memory, one of the things I didn't point out earlier is that the TRC on this device is down at 2.7 nanoseconds. So you have more than enough time to, in a packet time, for instance, to do link list operation, for example, to add packets in. And then maybe reserve the rest of the partition then for your table lookup operations, which of course then have to be bank aware. They have to stay out of the regions that you're doing your linked list in. And that would allow you then, for instance, to do a 400 gig or 4 times 100 gig type processing in this application. So again, something for you then to look at later in your handouts here, but showing some of the different ways then, because we build a lot of flexibility. These are individual, independent type commands. They have some restrictions on how you can issue them, but you can mix and match and balance the various commands. So you can see here as an example, we've got a read, we've got a write here. So this was the traditional one that I just showed you earlier here. Here is a command where we do a read, actually 2 reads. We have a write here, and we have a 36-bit write as opposed to a 72-bit write. That then allows you to saturate the output port in terms of reads, so a different set of commands. And here's another native example. And you can see here that with this now we can get up to 4.5 billion accesses per second, the I/O being the primary limitation. So again, if you remember, we have 6 billion accesses internally. We only get to use about 4.5 when you're running it into these various modes. So we have read and write 72 bits. With this, we have write 36 bits, which makes more efficiency on the interface, because if I only want to transfer 36 bits, I don't want to waste the other 32 bits of bandwidth, which allows us to get up to this higher level. But we started to go further beyond this, and so when you start looking at the next device, the 820, then we start to add things like burst commands, where you just send in the address and followed by streaming data going in. So that's one enhancement that we made within the architecture. So if you look at just using these various commands and you look at the memory, you can start to compare what this means against other networking type devices. It's kind of interesting to look at the shapes of the curves here. If you look at RLDRAM 3, for example, it's got just an I/O bus that you either have to be writing into it or you have to be reading back out of it. And so what happens is when you start getting to the point where you're doing heavy reads and writes, it reaches its minimum performance, because you also have to do bus turnarounds and you have to have some gaps between reading and writing the blocks themselves. If you look at QDR-SRAM, it's got separate I/O coming in, the address and the data coming in, and then it's got data coming out, which is more similar to actually our architecture and what we do. And it reaches its maximum point at the 50/50 point. And you can see that with these various devices that are shipping today, the maximum throughput in terms of accesses per second are hovering around this 1 giga access sort of area. So when you start looking at what we're achieving, first of all, with the first generation bandwidth engine we talked about 2 years ago, here the maximum is at 2.75. And this, depending, the reason for this is in that particular architecture, the optimal point was 2 reads and 1 write. You can see here that with the 720, the second generation, using that same sort of commands, you can get to that point doing 72-bit commands. But when you now add in the 36-bit commands, we can reach up to the 4.5 giga access. Now this chart is using the 15 gig SerDes on the I/O. So now I want to shift to the other device, or 2 devices in that family, but we'll talk about the 820 because it's the most featured device. And this one's really talking about getting more with the same amount of I/O. Because if you remember, we talked about 4.5 giga access. The device internally can do up to 6 giga access. So there's actually bandwidth that's left over internally. So with the 620 device here, you can start addressing a lot of other applications. We added things like statistics, so an onboard ALU. I'll talk about that a bit more. You can do metering type operations or dual operations. We'll touch on that. We've even added some atomic operations where you can do things where you can do a test for 0, and if it's 0, then you can write a value into it. So to start to do things that are transactional in nature. Each one of these typical operations, our philosophy here was to create a macro, which what we didn't want to do is dictate people's algorithms or structures, but we wanted to take some of the most common things like adding 1 to a packet count, or adding n to a byte count, for instance, and save the round trip traffic, or in the case of transactional, for instance, be able to close the loop down tight. And so if we could just save 1 transaction back and forth, then we've doubled the performance. If we could save 3 transactions across, then we've quadrupled. So here's the example then of what we're doing internally then for a counter. We have the ability to update a single counter, or in this case I'm showing a dual counter, where you send in a command that's got a particular offset into memory, which represents a particular flow in your table, and then can add 1 to a packet count and add n to the byte count, all in 1 cycle. So as commands are streaming in through the input port, what we're doing is we're reading the memory, we do an ECC lookup, or correct, check and correct, and then we do the appropriate arithmetic, and then we write it back in. So it's a synchronous, highly pipeline type architecture. So just by paying attention to how you're feeding this, you can then avoid collisions internally. The other thing that we did in this particular architecture that we didn't do in the previous bandwidth engine, so we've doubled the counters. The other thing we've done is we've added in the pipeline the ability then to look and do a feed forward. So if you fired in several commands into the same counter location, we'll feed the data forward and keep it all locally, so you don't have to bring it back out again or pay attention to looking into write buffers internally in your NPU. So the second area is the metering area. And this is following on the same sort of concept that maybe you have two counters that you want to update. But these two counters are different if you're familiar with metering in the case of packet processing. In packet processing, what you want to do is rather than count individual things, what you want to do is count things against time. And so it's kind of like bank accounts where you drop in credits, and then when packets arrive, you withdraw. And so those counters want to be maintained in time and then compare them against particular limits to decide whether you have enough to withdraw. And so we do a single metering and we do a dual metering. And what this does then is allows you to, where we use 16 SerDes to do 4.5 billion accesses per second, with 8 SerDes because of the savings in the density in the commands, and we can keep 6 billion operations available internal, so we can saturate the internal architecture. So a little bit about the physical design now. This is something about, talking at the higher level, what does this thing do? If you look internally, we've paid a lot of attention to the latency through this device. Because no matter what, people always talk about, I can always cover latency. Well, you can cover that by adding more threading. But as that latency goes up and the packets get smaller, then we have to do a lot more threading. So complexity can grow. So what we wanted to do here was to minimize the latency. In the BE1 device, the first generation, we're at 16 nanoseconds roughly. With this device, we're in the 12.5 nanosecond. Part of that was by going from 10 gig to 15 gig SerDes, internally going from 1 billion, 1 gigahertz internally to 1.5. So some of that came out from that. But then you can see architecturally some of the things that we did where we added an ALU internally now that has 2 inputs, so we have a lot more feedback bandwidth within this. And we also have this bank conflict resolution logic, so it has a feed forward type. So there's a lot more performance is happening within the core of this device. And for you that didn't see the previous presentation here, primarily what we do is we come in through the SerDes, we come right out of the SerDes, the raw interface, and then do a deserialization and dump that immediately into a slip buffer to line up the different lanes and then into commands. And we do that all within less than 2 nanoseconds from the SerDes input to hitting the memory interface itself. So a very low latency structure. A lot of that's due to the way we pick the particular protocol and the fact that on the SerDes we're only taking advantage really of the analog front end and then immediately going into a parallelizer. So the last slide I wanted to show here talks a little bit about, what is the cost of some of this different logic that we added. Because a lot of people say, well, gee whiz, serial, isn't that going to take up a lot of your chip? Well, when you look at NPUs, and you look at the I/O rings around that, typically I/O rings in an NPU can be as much as 20% of the die. And that can happen in some of the, the high-end memories, so you have to be really careful. In this particular case, the SerDes themselves are only taking about 5% of the die. And if you look at the protocol itself, that's probably another 1% or so, 2% of the die. The rest then is in the functionality area. The other aspect that looking at this is people would say, well, you added these direct map caches, how much is that taking up the die? And that's probably about 10% of the die, I would say. But think about it. If you were to implement this all in 6T memory, which is what you would have to do for QDR type SRAM, this die would be about 3 times its size. By adding these 4 caches, we were able with a 10% adder to get the performance of something that was about 3 times larger. And so we deem that as a good trade-off then of being able to double the bandwidth in the worst case type applications where you're doing both reads and writes. So thank you. Questions? Any other questions? Oop. I don't juggle very well.
Well, thank you very much, Mike. Okay, next up we have a talk by Netronome. We'll have 2 speakers here. We'll first have Sakir Sezer. He is the Director and Head of Network and Cybersecurity Research at Queen's University, Belfast. He is co-founder and CTO of Titan IC Systems and also fellow of Netronome. Our second speaker for this talk is Gavin Stark. He's the CTO of Netronome. And he says here in his bio, he's a software guy at heart. He has been architecting and designing network processors for 20 years, starting during his PhD at Cambridge University, with a performance range of 10 megabits to more than 200 gigabits per second. Gavin was previously Chief Technology Officer at Basis Communications, which Intel acquired in 2000. And at Intel, he was responsible for the IXP product line, the network processor product line that Intel had. At Netronome, he has architected the NFP32 series and today's NFP6 family that the talk is going to focus on. Please welcome Sakir and Gavin to the stage.
As the chairman introduced, divided in two parts. The first part is basically, oh, it's not working. Sorry about this. My thing is not working, so maybe take it. Okay, the first part is to introduce you and give you an overview about software-defined networks and the challenges of software-defined networks. Second part is to introduce the network flow processor, the next generation NFP6000 series called the Harrier, and then talk about the application relating to this. It doesn't work. All right, sorry, thanks. So when we start, before we're explaining what software-defined network is, who doesn't know anything about software-defined network? Can somebody put up? Quite a large number. Usually, software-defined network is basically the hot topic in Silicon Valley everybody's talking about. And everybody will tell you a different story about software-defined network. So I don't want to really go in details. So I have put my interpretation of software-defined network in these slides that you can see. So it is a definition for evolution of IP networks. So what we see in networking is before we had networking, but now we have invented cloud, and everything goes to the cloud. And the nature of how we communicate has changed. So first, we have a communication between the individuals to the cloud, and then within the cloud. And within the cloud, there are different service providers, different applications, so on. So what we can also say is a paradigm for converging networks and cloud computing. This is another definition that match SDN. But technical people like ourselves here, they would say, okay, SDN is actually the virtualization of the network, the ability to provide switch as a service. So in this case, access. But there's also more clear technical definition defined by Open Network Foundation. And this is something I would like to go more in detail. As you can see in this three-layer architecture, the Open Network Foundation defines the application layer, the application, basically the business application that people offer cloud application. It interacts with the software layer. The software layer, it's an intelligent layer that deals with the request from the application to configure the infrastructure, the switch layer. According to the Open Network Foundation, the switch layer is also referred to as a bare metal switch layer. But in reality, the switch layer has to do a lot of things. And from an SDN perspective, there are a number of challenges. And one of the challenges, performance versus flexibility. We have to deal with extreme high traffic, multimedia traffic. The bandwidth is still increasing, and quality service has to be provided. We have to deal with scalability issues. That means such software-defined network has to operate at 100G and beyond. Third, security. As we know from past, security has always been a challenge. The main security challenges has been how we deal with malware that infects compromised machines. Second, how we deal with denial of service attacks. Both are applicable for software-defined networks. If the control layer is a software, then it can be compromised. What happens when the software controller is compromised? Second, because the software, we can also apply denial of service attacks. So security is a major challenge that needs to be addressed. Interoperability is another challenge. Obviously, we can't switch off the current network and then switch on software-defined network tomorrow. So there is a way that this transition has to go over several decades in some instances. So because we are all technologists here, and we are looking at mainly the chip design, so the main challenge from an SDN perspective that we're going to talk today is the performance relating to the data path. And in this case, the data path has to be addressed. So two main challenges here are the SDN must facilitate complex packet and flow processing capability. And that has to be programmable. So it is not bare metal switching. We have to embed programmability into the data path. Second, the SDN has to deal with the services and applications and their demands to configure the network. In this case, the switch, the data path has to provide all these requirements, whether security, quality of service, load balancing, and so on. So there is a certain requirements uniquely from silicon at the SDN layer that needs to be met. And looking at past processing technologies and network processing capabilities, I think we can divide this into 3 points. And use another pointer. These 3 points are first, highly threaded into a heterogeneous processor architecture. We have to deal with different requirements. It has to be highly threaded because the smallest unit is a packet, and then we have another unit called the flow, another unit called the sessions. Second, we are dealing with data-centric problems. So we have memory and I/O-centric issues that we have to challenge. So the network itself has no arithmetic function as such. It is basically moving data from one place to another. So I/O and memory is extremely important. So this has to be addressed dealing with flow and session-related processing. The third one is deterministic on-chip processing. So latency is an issue, and throughput is an issue. So we can't afford to have highly cached architectures. We can't deal at the lower data path with coherency or data duplication. We are using this type of application at the moment in order to achieve the throughput, but these are main challenges that needs to be resolved for SDN for higher data rates beyond 100 gig. So I'm handing over to Gavin.
Thank you, Sakir. So Netronome now has had a flow processing vision for almost 10 years, and it's nice to see that some of the industry is catching up. Really, SDN is about putting packets into flows, and flows have defined paths that are managed by SDN controllers. The approach to implementing a good SDN card or application is you need a high-performance CPU, an x86 CPU subsystem or something like that, and you need something that manages the packets into flows. Netronome's first products were just card-based, so they were driven by an x86 with an IXP and an FPGA that basically let the x86 be part of the data plane. The first chip that Netronome produced, we licensed the Intel IXP, and that was the 3200 family, and that's now a few years old. And now we're talking today about the 6000 series. The 6000 series has got up to 200 gigabits of processing capability, of packet processing capability. We've increased the number of cores. We have 200-odd processors on the thing this time. Memory bandwidth has gone up. We have internal and external bandwidth, or external and internal on the slide. We've got, as far as the processors are concerned, they can get 7.4 terabits of memory bandwidth. The internal memory bandwidth is much higher than that. But in terms of actual data throughput, there's 7.4 terabits inside this just internally. And we've now reached 3 billion transistors, which is big. It's nice to see it's not as big as everybody's chips here, because you don't want to be quite the biggest ever, but it's manageable. basic outline of the chip, the functionality of the chip is described, is sort of shown in this slide. We have MAC interfaces, which are on the top left, how the packets get in on the bottom left. These feed through islands. You see that there are sort of collections of things. Those are islands. I'll talk more about those in a moment. But the packets feed in through these packet processing islands, which do a first level of packet to flow. There are then the flow processing cores. That's the second column there, which is a set of islands that are latency-tolerant processors based on the original IXP microengines. The third column is sort of accelerators. We have security. We have access to Interlock and LA for external TCAMs and the like. And the right-hand side, you'll see at the bottom there that there are 4 PCI Express interfaces, Gen 3 X8. We are part of the data plane with the x86 subsystem, and we're expecting to connect up to multiple x86 cores. The other bits on the diagram, there are memories, external memory units at the top right, which connect up to external DRAM, and an internal memory unit on the left. And the other bits I just want to highlight is inside the islands, you'll see small blobs that say CLS and CTM. There are a lot of memories distributed around the system, and I'll be talking more about those as well. First, the technology bit. We're on Intel's 22-nanometer SoC process, and to be honest, this isn't really big news. It's a good process. It goes. It's got a standard flow. It works. This is good. We are at 3 billion transistors, so the upside to 22-nanometer is we can do that without it being cost prohibitive. But otherwise, well, it's a good process, and we are basically happy with it. This diagram shows the actual floor plan using those islands. The colors, you'll see the yellow or cream color is the area that's always on. It's power domains, basically. The blue stuff is crypto, which is the second power domain, and the gray, I suppose, at the bottom left is a third power domain, so we can have a few products. But really, if you look at this, you'll see that we're not really building a 3 billion transistor chip. We're building 30, 100 million transistor chips, each of which is an island. And we do try to separate it into this. What is an island? An island is roughly 100 million transistors. It has this overlay on top of it, which you can see is sort of shown in the middle there. Every island has the same overlay. It contains data buses, control buses, so on and so forth, JTAG, clock distribution. You really can treat it as a separate small chip. What this means is that even though we've invested heavily in sort of internal knowledge in using the Intel 22-nanometer process, we can leverage that for future chips very easily at the GDS2 level by picking up the islands we've got, rearranging them just like Lego, and producing another chip that maybe is only a 40 gigabit chip or one that has 8 PCI interfaces for a data center, different data center application, and so on and so forth. The one important aspect to this is that, as you can see, you are a number of clock ticks from one place on the chip to another. So we need a latency-tolerant processing architecture. Underneath, in order to cope with this. So we're not a cache-friendly architecture. We don't do caches. The upside to that is we store data once in one location. We never have to duplicate data. We get good silicon utilization. But, and we do kind of regard latency not as a problem here. It's an opportunity. The other thing that this drives is we don't process within the CPUs all the time. Sometimes we process within the memories. Just to show you what the buses look like, we do separate data, status, and control and test. The data buses, you can see on the left-hand side, we have a switch fabric with 6 ports on every island. The islands layer in a staggered fashion, and you can route from one part of the chip to another part quite easily, configurably at load time. There's a latency of about 4 or 5 clock ticks across an island. The event system is done with rings. It's a separate bus system. Control is separated. By doing this, we can manage the system much more easily and make those small 100 million transistor chips work, and we can plug and play them. And as I said, testability and JTAG is separate as well. What do we mean by latency-tolerant processing? What we mean is that we have CPUs, basically things derived from the Intel microengines, that are multi-threaded, that have multiple large register files, which can issue multiple commands to the memory subsystems at once, post them, and cooperatively deschedule. It then also means that we have these commands that go to these processing memories. The processing memories then will be multi-threaded because they have many transactions being given to them by many cores, and they're multi-threaded, and they perform operations close at the memory. The cooperative multi-threading means that the code in the microengines and the flow processing cores can cope with 50 to, if it's a DRAM miss, or a cache miss to DRAM, to 500 cycles. And by cache miss there, I'm talking about the DRAM optimization cache, just like the previous presenter talked about. They've got caching subsystems. It's an optimization, just like the PAM8 has. The processors we have, when the packets come in, they go to the packet processing cores. It's a very simple CPU. It's described here. It's stateless. The bulk of the work is done by the flow processing cores, which are shown in the bottom side, which is based off the Intel microengine. So do look at the pipelines. We call the microengines flow processing cores when they're coupled into our hierarchical processing memory structure. This is, if you bring you back to the block diagram, we had CLS and CTM inside each of these islands with the various accelerators and the flow processing cores. This hierarchy of memories, the local scratch is a scratch pad of 64K that has a processing unit inside it that performs, I think, 100 different processing operations, a bit like what Mosys were just talking about, at a gigahertz on 64K. There's a next step up, which is a slightly higher latency, which is the CTM, which does more operations, 250. It's multi-threaded. It's got a terabit of bandwidth inside its memory and so on. The next level up in the hierarchy is the internal memory units, which are 4 megabytes. They do even more different processing operations, things like statistics, lookups, very complex atomics. And then we have on the top right here, we have external memory units, which again have the same sort of capabilities, highly threaded. But here, the memory is backed by DDR. So the chip supports 24 gigabytes of DDR, but really, you end up using the internal memory as much as possible. This slide shows us what we have in one of those threaded processing memories. They all have an interface to the fabric, bit on the left. There are then a number of engines, which each have their own pipeline, and these talk to a multi-banked SRAM. So we have, every SRAM we have has got these eight banks running at a gig, and we can change the pipelines in and out in different places. So when I say the internal memory unit does some set of operations, the external does a different set, we're putting in different engines in the middle. An engine is a highly threaded memory engine, is interfaces into the previous subsystem, a pool of threads. The top, we have 16 to 64, depending on the engine. If the engine is doing very simple things, lowish latency to its SRAM or a small pipeline, may only have 16. But for just plain bulk read and writes and more complicated, some of the higher throughputs, we have up to 64 threads. There's then a application-specific pipeline. So here we're showing that, I suppose, the atomic engine pipeline, which has 3 stages in its ALU. So it can do arbitrary operations on 64-byte cache lines. So arbitrary, I mean it does locks, it does queues of locks, it supports memory lock transactions, hash table lookups, atomic adds of hash table entries into a hash table. It does queuing for threads. It's got 200 plus operations that it will perform. We have in the chip, we have 7 different engines. And if you look at the total number of operations we can do, I think it's roughly about 200 billion operations per second if all of the engines were running simultaneously on the chip. Finally, for me, we have a lot of good processing in memories. We have a lot of good processing in the flow processing cores and in our packet processing cores. But sometimes hardware accelerators aren't still the right way to go. So we have bulk cryptography engines. It's 50 gigabits of bulk cryptography, AES, DES, SHA-1, SHA-2, the alphabet soup of cryptography. You expect to feed that through the FPCs. Hash engines, again, very useful to have. Actually doing those in instructions can be tough. You want to fire off maybe a packet header to a hash engine, and you just want to get the hash back. So we've got some sophisticated hash engines on the chip. Traffic management, packet modification, pretty simple processes, well-defined processes that can be managed easily in hardware. We've got the lock handling and statistics in our processing memories. And we have string matching, regular expression technology as well, sitting in accelerators in the hardware. Finally, the bottom left there. Yes, indeed, the bottom left. You'll see the data distributors. This is our interface into the x86 world. As I said earlier, it's critical that we are basically a flow manager for multi-socket IA. So our data distribution to 4 PCIe X8s is critical. We support 256 endpoints. Very interested in all this PCIe switching, but we also just try to switch. So I try to deliver from one PCIe interface directly to a single x86 core subsystem.
Thank you, Gavin. So I will give you a bit overview of the applications that this processor Harrier can be used. As Gavin emphasized, obviously the multi-PCIe interface at the processor opens up a lot of opportunities for heterogeneous processing. But from a SDN data path perspective, obviously the engine itself are efficiently and effectively used for quality of service with specific pipelined operation within the micro engine. It can be used for virtualization. It can be used for load balancing. And specifically from SDN H switching perspective, flow classification, treating the flow, managing the flow, and also the ability to be programmable by a software-defined network controller via link onto this device. Second application is obviously intelligent network interface to this PCIe interface. This allows the combination of this device to do basically specific processing. And the next slides may outline more in detail this. Obviously, if you have a 200G traffic coming into this device, you do the packet processing, you do the flow processing, and afterwards, based on application and needs, you can outsource to a different x86 with specialized functionalities. So this is more an outline how this can be done and in use as a heterogeneous processor for SDN. Finally, because of flow processing, this is also applicable to cybersecurity and any type of network security, specifically for next generation firewalls. It has the ability to isolate traffic. It has the ability to divide the traffic and extract information from the tunnels that you want to more in detail analyze from an application perspective. But it can also do the content processing on this content itself and isolate. And this is applicable for a wide range of applications like web security and from a quality of service perspective, load balancing or providing the necessary analytics on the content itself for the individual queues or isolation of traffic. So this is more or less us. If you have any questions, Gavin and I are happy to answer you any questions.
Derek Chu from Microsoft in UT Austin. It's a very impressive piece of hardware. Can you say more about how you program it?
The PPCs we program ourselves for the packet classification. The FPCs are programmed in C. We have some coding styles, coding extensions, decal specs, and so on, which help you assign where particular structures are kept. You may want to keep them in local memory, in registers, or in a particular memory. But we have a fair ability in the linker and so on and so forth. But basically, you can program it in C. The code space is limited, but the application size is also meant to be kept small for 200 gig of processing.
Right. So it's really pretty. There's nothing fancy in terms of tools. It's pretty much microcoding it.
Yeah, it's not painful in C, but it's not as simple as so we say as just compiling snort. Yes, you do program for it. You don't just pick up some code and hope it will work.
Good morning. This is Michaela Bloch from Xilinx. Could you shed some light on power efficiency of the device? I'm absolutely in awe of the performance that you're getting out of it, but how about power efficiency?
There is an awful lot on the chip. It's difficult to use it all. And indeed, most of it, if you're really running a 100 gigabit, so if you're running a 100 gigabit simple flow forwarding device, which is shipping maybe IMIX type traffic, 200 byte packets, you're looking at there at about 50 million packets per second throughput. You're using probably about 5 to 10% of the device. So there is a lot of local clock gating. The clocks are pretty much gated everywhere. Small blocks, that would turn off the blocks. It's a hierarchical clock gating system. So if a processing memory has no transactions or a threaded engine has no transactions, the whole engine is turned off. For low applications, or if you're not using all of it, then we can power down the memories. But the trade-offs, we look at trade-offs for light sleep, deep sleep, and so on in memories. And realistically, the time taken to get in and out and the benefits, Intel's 22 is not that, it's pretty darn good from a power perspective. It's not that leaky, particularly the SoC process. So we don't put things into deep sleep or light sleep or anything like that. It just turned out not to be worthwhile.
And on a small technical detail, what's the maximum number of flows that can be supported? The previous generation, we were doing 1 to 10 million flows. Here, we're doing 10, 20, 40 million flows simultaneously. You have to maintain, I think my biggest issue with how many flows can you do, it's, well, how big is your DRAM? And how much state you're going to store for each one? As soon as you've got to the point where you're trying to go off and fetch things from DRAM, you're limited by the DRAM transactions, and it's just a matter of storage. So, yeah, if it's flows of that form, then 10, 20, 40 million, not a problem. Welcome.
Mark Miller, Tabula. Gavin, I was wondering if you could add a little bit more color on the islands. In terms of that hexagonal structure, how much of it is uniform with, let's say, PPCs, and how much of it is intermixing PPCs and flow processors and some of the other hardware in the chip?
So the islands, if you go to the block diagram, you'll see that there are little sort of bluish, rounded rectangles, I suppose, that show you what's in an island. There are FPC islands. An FPC island is 12 microengines or 12 FPCs, the cluster scratch, and the CTM. That is an FPC island or an ME island. The ARM island, for example, throws away or doesn't have 8 of the FPCs, but it has a 256K L2 ARM 11 in there. So we trade it out, but that's an island. The PPCs are in the ingress NBI processing unit, which does the ingress processing for packets, classification, buffer allocation, and then DMA and that sort of side of things. And it does egress, quality of service, and so on. So the PPCs come with the ingress and egress. So that's sort of separate. That's how you get the sort of separation.
Thanks. It sounds like it follows the flow of your original diagram that shows kind of the vertical columns. Yeah. And you get 4 vertical columns. So it sounds like within each one of those has its island type. Yeah.
In the vertical column, for example, for the FPCs, there are 7 FPC instances, and the FPC island is an island instance type. The ARM is another. The crypto is another. The Intel Arc and LA, the PCIe, they're all different instance types.
Thank you, gentlemen, for a very interesting talk. Really appreciate it. And we will move direct.